Hi everyone! For my final project, I chose to rebuild an image using randomly placed pixels on a blank canvas, and I approached that with two different algorithms. One's just a simple greedy algorithm, and the other is simulated annealing. And I wanted to see how close I could get to replicating the original image and how fast and efficient each algorithm would be. So for each, I started with a blank canvas that was in the same size as my original picture, and I ran through a number of iterations, altering one pixel at a time at random, and each time I was trying to minimize the mean squared error between the picture I was working on and the original target image. So up here is my greedy algorithm. And here we have a helper function, and this calculates the sum of the squared differences between two pixel arrays. And then we cast the answer to int32 to make it easier to work with to avoid some errors. And our main function down here takes a few parameters, the original image path and then a file output path. And you can specify the number of iterations you want it to run through. So I chose a picture of my cat Jade, and it's not a very high-res image. It's pretty small and easy for the algorithm to handle. I chose that because I wanted to be able to A, perform it here in this presentation, and B, be able to test it fairly quickly. So obviously both of these would run a lot slower with a larger or more detailed image. Drag that there. Okay. So first thing we're going to do here is track the runtime. I wanted to see in seconds how long each of these algorithms took. And then we're going to load the image and make sure it's RGB, and then we convert it to a NumPy array to make the math that we use with it easier later. And then we just grab the height, width, and the number of channels so that we can create the canvas here in the same size as the original image. And then the current SSD is the sum of the square differences currently between our original image and the blank canvas. So we calculate how many elements we're working with on this image, and that's the number of pixels times the number of channels. And then we calculate the mean square error, which is the current sum of the square differences divided by the number of elements. And then we've got a for loop here. And that will run for the number of iterations we specified unless we hit an error of 0.000. So if we arrived at a perfect image before it's done running, then we're going to break. And at random, we select a pixel somewhere on the blank canvas. And then most of the time, that's the 0.95, most of the time we're going to try to match it to, on the original image, what the pixel at that spot is. But we're also going to throw in this kind of wildcard, trying a random color, which helps it avoid getting stuck in a local minima. And we're going to save the old pixel in case we want to revert, but we're going to see if that pixel and our change to it will help the overall accuracy of the new image. So here we're going to calculate how the change would affect the global error, and instead of recalculating everything each time, keep a running sum of squared differences and only update the relevant part. And so if the change reduces the global error, I keep it. And if it doesn't, I roll it back to what it was and move on to the next pixel. And that's essentially the greedy algorithm. It just kind of goes with what is the best choice at the current time. And then every 500,000 steps, I'm going to go ahead and print out a file showing like the progress. I'm actually going to start running that now. So you can see the MSE starts at 33,000 here, and as it runs, it's going to cut down exponentially on that error. And then for the rest of the code, I just kind of save a final copy and print out a user message and let the user know how long it took. Okay, so all the files are being generated over here. You can see like the first one is just a blank white canvas. And then as it runs, it's getting better. It gets better actually really quickly. That one's almost like perfectly clear. And you can see the MSE goes down like exponentially very quickly. So I actually found the greedy algorithm to be super efficient. I had 10 million iterations and it was no problem. It ran through them very quickly. I did check, if you use a higher quality image, it's obviously going to slow down and take a lot longer. But I imagine that would be the case for any program that you have to copy an image in this way. Greedy algorithms sometimes have the potential to get stuck in local minima. And if that happens, it may potentially have trouble processing or might leave areas on the image that aren't as clear as they could be. But all in all, I found this to be really efficient. So here it stopped like way before it ran into the 10 million. It stopped at 3 million and it had a perfect match. So let's check out that final result here. Yep, pretty much an exact match. You can see the one just before, it has a few like little pixels that are not quite perfect. But all in all, I think it really quickly achieved what I wanted it to do. Okay. So I'm just going to go ahead and clear out all of those images that we generated. And down here, what I have is the simulated annealing algorithm. And this one's got a very similar structure, especially at the beginning of the end. But instead of always rejecting the changes that make the global MSE worse, we're going to sometimes take a risk and accept them. And the acceptance isn't completely random. It also depends on a temperature parameter. And it starts off really high, meaning that it's going to accept high risk choices, and then it cools off over time. So you could see the setup here is the same. We have our helper function. We're taking in our parameters. A small difference is in the parameters. We're going to set the parameters for initial temp and final temp here. The algorithm needs those. And then we're also going to keep track of our time and take in the image here. Okay, so down here in the for loop is where the code really starts to diverge from the greedy algorithm. Actually, let's get this started right now because this algorithm did take quite a bit longer than the greedy algorithm to run. So while I run through the code, I'm going to get that started running down here. And it starts at this MSE at 33,000, which is, I think, yeah, the same as this one was there. So same calculations. Here in this for loop is kind of where the code diverges. We start by checking the temperature, and it starts out high, and then this function is going to cause it to drop over time. When it starts at high, basically that means that the program is more willing to accept less ideal moves, and as it cools, it rejects moves that do not appear initially to enhance the overall canvas. So it becomes almost more like, I don't know, in my perspective, it's almost more like a greedy algorithm at that point, because it's only going to accept what it can immediately see is a helpful improvement. Okay, so the same time as last time, we're going to check how much error does the old and the new pixel configuration have versus the target. And the delta error here is new. So this variable tracks how much of an improvement that the quick temporary change that we're doing here, checking that pixel that we switched, we're going to check how much of an improvement it actually made. So if the delta error is negative, that means that it improved the canvas. So it decreased the error and made the canvas sharper and more accurate. So if that happens, we're just going to accept it unconditionally. And if it's the best so far, we're going to save it to the best canvas. And the best canvas is essentially a snapshot of what we have currently as the best possible of all the answers that we were able to put together. Otherwise, if the delta error is positive, that means that the change actually made the canvas worse. So sometimes you want to still accept that move, especially early on when the temperature's high. And that just helps you kind of escape the local minima, and the algorithm sort of keeps an eye on the larger picture and, you know, considers that move for a while, even though it didn't seem like the most opportune move to make immediately. But the probability of acceptance goes down, and as it cools down, we're just going to reject it based on this like random number that we're testing it up against. And then if we reject it, we just go back to the old pixel value because we decided it wasn't worth the risk. If we accept it, we're going to update the tracking value. And once we're finished, the code is essentially the same. Every 500,000 steps, same as before, we're going to print out a file as we're doing over here. You can see already that these are running a lot longer than they did last time. And here the MSE went down. It went down really quickly, but you can see like over time it stopped the exponential decrease in error. And now it's just doing a very slow decline in error. And it looks like we're going to hit that threshold before we actually get to a 0 error. So let's see what we have. We have our original photo. This was the blank canvas that we started out with. This is actually one of the later ones. Let's pull this out so we can see. Okay, so this is one of the earliest, and it's definitely has a lot more white pixels on there. It's not as mature as some of these other solutions. So let's look at that. So that's already getting very good. But here we hit the number of iterations that we set. So we just stopped there. So 9,500,000 we should find, and it actually printed out the final result there. So that's how close it got. And it's not perfect. And it definitely took longer. So this one took 228 seconds, whereas this one here took 82 seconds. So simulated annealing is better than the greedy algorithm in general at seeing the larger picture and taking that into account. Basically, it jumps out of the local minima. Especially for very detailed images, I suspect this may be better to avoid errors. But the big con about it, though, is that it's a lot slower than the greedy algorithm. And sometimes you double back in steps, so it takes a lot longer, and it's a little less efficient. So you have to wait for the temperature to cool for the best results. I personally, for this purpose, like using the greedy algorithm better because it's a lot faster, and especially for this small image that I had, it seemed to achieve really good results. But I feel like the simulated annealing algorithm could potentially produce a clearer image, especially if you're using larger pictures, more detailed pictures with a higher resolution. So given more time, I would definitely like to test that out and see what are the benefits of the simulated annealing algorithm. As far as road bumps that I ran into creating this project, so originally I was going to use a genetic algorithm instead of the annealing algorithm. But at least the way that I implemented it, it took a very long time. Like it took a very, very long time, even on this smaller image, to produce any kind of change. And that made it really difficult to test. So I just decided to pivot with the time frame that we were given and try another way, and it did work out. Well, thank you so much for checking out my project. And if you have any questions about it, just let me know in the discussion below.